Hello, here are my responses for the quiz 3 for theory of computation. So for this first problem, where we want to make a Turing machine transition diagram for this language, essentially what I did here was have a system that marks each next letter in each section. Then once all those letters have been marked, with an X, it can just look if it's X's hash mark, X's hash mark, X's, and then it's good. So we do this by, for example, let's say if a letter is A that we're looking at in this first section, we'll mark it with an X, go through that section, go past that next hashtag, go through all the X's that have been marked in the second section, until we get to the next one. And if it's an A, then good, we can mark it. If not, it's bad, we can't continue. And then we continue going right after we've marked it, through the A's and B's, past the hash mark, then past all the X's in the third section, until we find the next symbol, which should be an A, and if it is, we mark it. And once again, if it's not, we ignore it and reject. And then we go all the way back left, and then we go right a little bit until we get to the first unmarked symbol in this first section. And we repeat this process, and it can either be an A or a B. So this B section does exactly what this A section does up here, but with B's instead of A's. And then if we actually do find that the first unmarked letter is a hashtag in the first section, then we see that hashtag, we go through X's, and we should see another hashtag, then we go through all of these X's, and then if we have done that, then we should see an empty tape section, and then we accept it. And that is pretty much what I say down here. Okay, so now question 2. So we want to see that reversal is a closure property. So let's talk through this. If W is a decider for the language L, then we can, if we can create a decider WR for the reverse of L, then reversal is a closure property for deciders. So we can do this by constructing this decider that reverses the tape before passing it into this original decider W. So if we do that, then that means that any string that is in the reverse of L will now look like a string that was in L, and since W decides L, then WR will decide the reverse of L. So essentially we just flip the string, pass it into the original one, and then take that result. And then it also works for recognizers because it will only get stuck in an infinite loop on strings that would be rejected from W sub R due to the reverse of those strings getting stuck in W. So there would be no strings that would get stuck that shouldn't be. Okay. Question 3. Okay, so we want to show that this is decidable. So essentially we just want to create that decider, and the Turing machine for that decider would decide if the language of the DFA that contains BBB as a substring is a subset of essentially this. So that contains BBB among others. So that's like the language of this. So we know it's pretty easy to create a DFA that accepts strings with BBB inside, and we know subset is decidable under the regular models, so BBB DFA is decidable. And to go into a bit more detail there, so if the language of this DFA that we created, the one that accepts BBB as a substring, is a subset of M, of the language of M, then we know that the language of M contains every string that contains BBB. So we accept M. Otherwise reject. And we had to do subset here because BBB DFA also includes among others. So there could be other strings that are accepted that don't necessarily contain BBB. So we just create that BBB DFA, and then we run that subset on it. So we just know that it does contain all of them. Okay, here on this fourth problem, so we want to show that triples TM is an undecidable language. So we're going to use this proof by contradiction, where this is the decider for this language, and we're going to use the ATM problem. So we have this accepts algorithm here. So we want to sort of reduce this inside of this. So we do that by creating a new Turing machine, M prime, such that the language of M prime is either triples over whatever language we're working with in all of this, or it's empty. So you can do this pretty simply. So if X is not a triple, we reject it. Otherwise, we can run M prime and return its result. And then on this whole Turing machine that we created, we can run trips on this M prime and return its result. And we know that this can work because it's easy to figure out if a string is a triple, which we did up here, using a Turing machine. But also, this is not, even though this technically should work, given our assumption, ATM is not actually decidable. So triples cannot be decidable. So this is a decidable algorithm given our assumption, but we contradicted it, so it doesn't work. And there's that proof.